Hi, everyone. Welcome to my talk. Today, I'm going to talk about our recent work on enhancing Presto's query performance and data management with Hudi, the innovations and future. A bit about myself. I'm Ethan. I'm currently a data infra engineer at OneHouse. OneHouse as a company delivers the universal data lakehouse architecture as a fully managed service. I'm also a Apache Hudi PMC member. I'm driving key initiatives in the transaction database layer and engine integration with Hudi. Before joining OneHouse, I was a senior engineer at Uber. So I built this near real-time analytics pipeline with Hudi incremental processing as a Hudi user to start with. This pipeline ingests large-scale data like TBs of data every day of mobile events from around the globe. So in today's talk, I'm first going to have a brief introduction of Apache Hudi, the open data lakehouse platform. And then I'm going to talk about how Hudi improves query performance with multi-modal index. And before concluding the call, I'm going to talk about how we enhance Presto Hudi connector and what's the future for Hudi with Presto. So Hudi was born in 2016 at Uber when it was going through a hyper-growth mode. We're moving from a warehouse to data lake. So the problem Uber had to face were challenging in terms of the scale and complexity because it demanded designing abilities such as transaction guarantees on top of the immutable storage. So to dive into the use case specifically, on these slides, you can see that the trip database change logs would need to be ingested into raw tables based on Parquet format. And every 8 hours, the job used to bulk ingest 120 terabytes of data, while the actual change itself would be less than 500 GB. So in this case, the downstream pipelines would be built off this raw layer, and those two recompute all the data every 8 hours. So the end-to-end freshness would be around 24 hours, and the ingestion performance was extremely poor. As you can see here, this is a massive waste of resources, compute, I/O, network, etc. And imagine a job failure in this situation that can cause cascading effects of cleaning up and retrying the jobs along the chain. So when trying to design a solution for this problem, the creators of Hudi kept asking different questions. For instance, can we consume only the changes instead of full recompute? This would drastically reduce the amount of data and compute needed to ingest every time. The next question is, can we design a way to absorb these changes faster into the table? And while the upstream change logs can provide just changes, can we efficiently query just the changes from the data lake tables? While all these are happening, can readers be isolated to not read partial or dangling or dirty data? These principles guided the core primitives of Hudi, observes the incremental reads and snapshot isolation. So with Hudi, serverless transaction layer with database-like abstractions for DFS compatible storage is built. Now observes took less than 10 minutes to capture only those 500 GB of change data. And the end-to-end latency is reduced from 24 hours to just 1 hour. So this propelled more and more use cases, and Hudi started to evolve rapidly from that time. Today, Apache Hudi is much more than just a table format. It serves as a comprehensive lakehouse platform designed for data ingestion and processing. So it's scripted with a wide range of features and services, as you can see here, and maximizing the efficiency of both writing and reading data. At the foundational level of this platform lies the data lake storage. This is where all data resides, storing prevalent data formats like Parquet and Avro. Upon this base, Hudi provides a transaction database layer. This layer is where Hudi's true power shines, as it offers multiple services, including table services, indexes, and concurrency control with ASIC guarantees, among others. After data has been successfully ingested from various sources like data streams, databases, and cloud storage, and this data is effectively managed, Hudi offers the ability to connect these processed data with popular engines like Presto, Athena, and more for different types of analytics. So by facilitating these integrations, Hudi allows for efficient and advanced querying of data. So Hudi is proven at a massive scale as a lakehouse platform. And as you can see the statistics here from actual production numbers. So ByteDance, TikTok, Uber, Walmart, and G all use Hudi for their mission critical applications. And for example, at ByteDance, Hudi is being used at exabyte scale for a single table. And even at this scale, Hudi brings analytics latency from days to minutes. So next, I'll talk about how Hudi improves the query performance with multi-modal index. One key to improving the query performance is reading fewer bytes from the table. To achieve that, indexes are helpful in this case for locating the records with small amount of index metadata and reducing our cost to improve query performance. So index is widely employed in database systems such as RDBMS and data warehouses to locate information quickly. This is similar to how index page at the end of book helps you allocate information. And such indexes are especially useful for queries that look up the needles in haystacks, as only a few selected records need to be returned in this case. Hudi uses indexes to locate record efficiently and not only on the read side, but also do fast updates. So with index, Hudi is able to merge each file with updates and deletes only for that file. So this significantly reduces the I/O for merging data. As you may already know, Hudi supports different types of indexes such as Bloom filter-based index, the H-based record index, and more. So to efficiently manage and fetch index metadata, the multi-modal index in Hudi is established. And this multi-modal index is used on both write pass and read pass for efficient upserts. And the read pass is for faster queries. So if we look at, for example, what happens behind the scenes when executing a query, the first step involves fetching the metadata, followed by query planning, applying some optimizations, and then eventually reading the data before serving them. So fetching the metadata is key to improving your query performance. And in Hudi, the multi-modal index serves this purpose, and it is structured as a metadata table with partitions supporting different types of indexes, such as file listing, column stats, Bloom filters, the new record level index introduced in 0.14, which I'm going to talk about next, and also the new functional index introduced in Hudi 1.0, which I'll also briefly introduce later in the talk. So all of these different indexes can also be built asynchronously in Hudi without blocking ingestion. So the record level index is a new index introduced in Hudi 0.14. Before its inception, the challenges are that for fast record lookup, H-based index serves the record to location mapping. And the problem is that a separate H-based cluster needs to be maintained, and H-based is known for operationally difficult to maintain and scale for throughput. Also, that requires dedicated resources and expertise. So the record level index comes to the rescue to solve this problem. By design, the record level index stores the key to location mapping, just like H-based index, but it's directly stored as a table level metadata. So to realize that, a new partition named record index is created internally to store this mapping in the metadata table. And the index metadata is stored in a few file groups instead of co-locating with other data files. So in this case, it drastically cuts down the cost of file I/O. And the record level index directly leverages the metadata table for fast index update and lookup. So the metadata table is an internal MR table, which provides uniformly fast updates for different index metadata. And the H file format of the metadata table unlocks fast point lookup, and that applies to the record level index as well. So now let's look at how the record level index metadata is organized on storage and how it unlocks the fast lookup. So as I already mentioned, the record level index is stored in the record index partition, and it has multiple file groups, just like normal Hudi table. And each file group contains multiple file slices, and the latest file slice reflects the latest snapshot. So given that metadata table uses each file as the base file format, as mentioned, so each file contains based on these key value pairs as a record for the key to location mapping. And let's say if I want to look up set up record keys. So in this case, first we derive the file groups to read by using the hash function of the applying on these file record keys to identify the file group ID. Then these keys are looked up in the H file through the point lookups without having to scan the whole file, which is more efficient. We have done a few performance benchmarks on both read and write on Spark to demonstrate the performance benefit from the record level index. So in the first case, we have 1 terabyte dataset, and each write batch has 200 megabytes of random updates across the table. And we compare the performance of record level index to the global simple index, which is the best for random updates before we develop record level index. And we can see from the result that the index lookup latency is reduced from around 20 minutes to just 1 minute after using record level index. And this is because it only has to read like metadata from a few file groups as mentioned from the metadata table. So it's more efficient than scanning all the data files in the global simple index. And this contributes to overall like 2x improvement on the override latency. And next, we also measure how the new record level index improves the SQL latency with point lookups. So we use the store sales table in the TBCDS 10 TB datasets, and we run 2 types of query. The first is select star particular record key, and second is the delete operation of particular record key. So by using record level index for filtering, we see a 2 to 3x improvement compared to not using this index. So this shows how record level index can give a great performance benefit on both read and write side. We have written a blog on the record level index. Please check it out. It discusses how Hudi enables the blazing fast indexing on large scale datasets. So all of these are great, and as I showed that Hudi provides powerful indexes. So now let's look at how we enhance Hudi support on Presto with Hudi connector to be able to use these indexes. So at its core, reading metadata table and enabling fast point lookup requires this H file format. So in Hudi point 15 release, we introduced a new H file reader to make the engine integration much easier. So first, we have written an H file format specification that defines the H file format required by Hudi. And this allows H file reader and writer implementation in any language, for example, C++ like native reader or Rust, by following this spec. And to make Java-based implementation easier, we have implemented a new Java H file reader, which is independent of H-based dependency or Hadoop dependency. So this H file reader is backwards compatible with existing Hudi releases and storage format. And the Hudi connector in Presto will use this H file reader to support reading different indexes in the future. As we are adding new capabilities in the 0.x, Hudi 0.x release line, the Hudi community has also pushed out like a bold vision for our next big release line, the Hudi 1.x. And we reimagine Hudi in Hudi 1.x as the transactional database for the lake with the polyglot persistence, raising the level of abstraction and platformization even higher for data lakes with Hudi. So if you look at what Hudi already provides, so Hudi provides functionalities like access method, log and log manager, utilities, and different services that are core component in database system. So on the left side, there is this diagram for core components of a typical database system. On the right side is how we structure components in Hudi and how Hudi integrates with different engines. So you can see that there are client communication manager on the top and process manager, relational query processor, and transactional storage manager at the bottom, and also the share components utility on the right side in the database system. And if you look at the right side, so the components in green is what we already have. And Hudi 1.0 envisions the experience on data lake or lakehouse to be a database like by providing like the same components even around like the existing ones. So as you can see here, basically different engines like Spark and Presto can bring the components in blue like query parsing, query rewrites within like the query processor, and all of these SQL code and frameworks for integrations or interactions with clients. So in 1.0, Hudi will be adding new components in yellow, such as better integration or enhanced integration with Query Optimizer and Plan Executor to improve the query performance. So in 1.0, we are also going to add new advanced indexes so that query engines like Presto can benefit from this. So as we already mentioned, advancing indexing subsystem and multi-modal index is core at Hudi 1.x. And we have already added 2 new indexes in the 1.0 beta releases. So the first one is the functional index. So this allows users to create indexes on functions or expressions. So on the high level, the context is pretty simple. So just like how you can create an index column, so functional index allows you to create an index on a functional column or an expression on a column. But efficacy of this functional index goes beyond what simple index can do. So let's consider a case where, let's say, stream of events from microservices in the backend are ingested into like a raw event table. And each event log contains like a timestamp column, TS, and associated organization ID column, like or ID. So in most cases, the queries on the table are organization specific, fetching logs for a particular time range. So a user may attempt to physically partition the table or data by both the organization ID and the day string of the timestamp. So in this case, let's say for a year of data and 1,000 organization ID, this generates like more than 300,000 partitions. And in most cases, the data can be highly skewed because only a handful of the organizations having majority of data, and other organizations having less data. So this partitioning scheme can lead to many small files. So in such case, if we use functional index, it can drastically reduce the small file data file problem, while still providing the data skipping, because now we can build the index on like the day string of the timestamp column using the functional index. So this is how functional index is performed, because it absorbs the partitioning into indexes, and there's no need to hide or evolve partitions. So other than that, we also introduce a secondary index in Hudi 1.x. So the secondary index allows users to do point lookups on non-key fields more efficiently. So this is coming up in 1.0 beta 2 and the general available of 1.0 release. So here is what the roadmap looks like for this year. So we are pushing the 1.0 release to be generally available in Q3 this year, and adding more indexes and support for unstructured data vectors and vector index in the new 1.x releases. And we are adding and providing Prestissimo support in Q3 this year in Presto Hudi connector, while adding other index support like with ROI and integration with Hudi 1.0. So the DML and DDL support is also under discussion. We'll likely pick it up in Q4. So as always, Hudi is community driven. We love new people to come join us. And here's the QR code to join Hudi Slack and ask questions on Hudi. And that's all I want to share in today's talk. Thank you very much. Love to answer any questions asynchronously. Thank you, everyone.